Hi everyone. In this last video for electric fields, we're just going to recap all the equations that we've used and just quickly recap the ideas that were presented in this topic. So here are basically all the equations that you will need when you are dealing with these electric fields. Okay, so you've got electric field of point charge. Okay, so you've got, some kind of point charge, either positive or negative, and is exerting its field out into the space around it. Okay, and if you want to work out the field strength at some distance r, so that's r, from that point charge, you straight up just use this formula. Okay, nothing to it. If you would like to know the force that a charge would feel or experience due to an electric field, okay, you just need to know the value of the electric field at the place where the charge is and just multiply the charge by the electric field strength. Okay. Alternatively, if you've got 2 point charges, say Q1 and Q2, and you want to work out the electric force between those 2 charges, then you've got an equation to do that. Okay, so don't get confused between this equation and this equation. This one is a more generalized sort of equation that can be used so long as you know the magnitude of the charge and the electric field strength of where that charge is at that moment in time. Okay, that will tell you the force that that charge would experience. This second one here, this is the electric force between 2 point charges. Okay, so don't get confused between those two and which situations to apply them. We can also look at this equation here, the work done on a charge by a voltage, and this will pop up most of the time when you're dealing with parallel plates. Okay, so there will be a potential difference of voltage across the plates, and you've got a charge moving from one plate to the other, I guess you could say, and you're trying to work out, well, what's the change in energy of that charge. Okay, it's either going to accelerate, say if it's a negative charge and it starts at the negative plate, it's going to get repelled or attracted towards the positive plate. It's going to gain energy. It's going to gain kinetic energy. Alternatively, you could start your negative charge at the positive plate and you can flick it up towards the negative plate. Okay, and if you give it enough energy, it'll be able to reach the other side. The energy required for it to reach the other side is Q times V. Okay. In deriving this equation here for the electric field strength between the plates, we had to remind ourselves of the work done as a force is being applied over a certain distance. You can go back and look at those notes, but basically use that in conjunction with this and you produce this equation here, which allows you to calculate the electric field strength between 2 oppositely charged parallel plates. You only need to know the voltage across the plates and the separation distance, d. Okay, so that's a summary of the equations that you looked at in this topic. Okay, that's pretty much all you need. Just also want to compare the gravitational and electric fields. Okay, there were a lot of parallels between these 2 fields. Okay, especially when you consider point charges. So recall for gravitational fields, if you've got 2 masses, you can work out the force of gravity between the 2 masses using this equation here, where r is the distance from the centers of mass of those 2 objects. Compare that to the electric force between 2 point charges. Okay, they look very similar. The formulas are very, very similar. Okay, and it's due to the symmetrical nature of point charges and spherical masses. The more general form of the force for gravitational forces is it's a mass multiplied by the strength of the gravitational field where that mass is in space. Okay, compare that to the electric force where you've got a charge multiplied by the electric field strength at the point where that charge is. Okay, this is a more general form. It can be used anytime you know the electric field strength. Alternatively, this one over here for the gravitational field, you can use that anytime you know the value of the gravitational field. Okay. and just comparing the equations for looking at the field strength for gravitational field strength. Okay, if you are at some distance r from the center of mass of this mass here with big M, okay, compare that to the electric field strength when you are a distance r from a charge that has a magnitude q. Very, very similar equations. Okay, it's just, again, due to the symmetrical nature of the spherical point charges and the spherical masses. It just so happens to be set up that way. Okay, so what are some differences though? So with gravitational fields, there's only positive mass. Okay, there's only one kind of mass. Okay, so there's no negative equivalent. Gravitational fields are always attractive. Okay, whereas with charge, you can have a positive or a negative charge. Okay, and that will determine whether the field is going to be attractive or repulsive, depending on the sign of the charge and the type of charge that you place in the field. Okay, if you put a negative charge in the field exerted by a positive charge, the negative charge will be attracted and move towards that positive charge. Or vice versa, if you put a positive charge in the field created by another positive charge, it will get repelled. Okay, so it just depends on the signs of the charges. Another thing is gravity is really, really weak. Okay, if you think about the equation for the gravitational field strength, okay, this value here, big G, that's 6.67 times 10 to the negative 11. That's a really small number. Whereas this value for K is 8.99 times 10 to the 9. Okay, so the gravitational field is actually much weaker than the electric field, or the gravitational force is much weaker than the electric force. But the really big masses that are involved with gravitational fields, that sort of makes up for the fact that gravity is so weak. Okay. Alternatively and conversely, if you're talking about the really, really strong electric force, normally the charges are really, really small. Okay, so overall things sort of balance each other out, and you end up with situations where you need to have a lot of charge to notice the fact that the electric force is really strong, or you need to have a very small mass to notice that the gravitational force is really, really weak. Finally, we know that some objects can have zero net charge. Okay, for example, atoms. Atoms themselves, so take hydrogen for example. Hydrogen has one proton and one electron orbiting the proton. Okay, so overall the charge of a single hydrogen atom is zero because the proton and the electron charges cancel each other out. But things will not have zero net mass. Okay, things will never have zero net mass. If something does have zero net mass, then it just doesn't exist. It's not there. Things like photons and stuff, that's another story. We won't go into that. But there's no way that you can sort of counteract mass with anti-mass. Okay, at least not for the purposes of Year 12 physics. So there you go. Those are just some differences between the electric and gravitational fields. It's nice to know that there are some parallels between them as well. Okay, as indicated by these equations here. All right, so that's it. That's it for the topic. We'll stop there, and next time we'll start looking at some magnetic fields. All right, so I'll see you then.